Well, last time I gave you some introduction to spectroscopy. Okay, so we discussed about what spectroscopy is, then the different types of spectroscopy. Okay, different types of spectroscopy, then how we represent the spectrum. We discussed all those things. Okay, so normally how we represent the spectrum, say along this axis we put energy of radiation. Energy of radiation may be in terms of wavelength or frequency or wave number, and along this axis we put intensity of radiation or absorption of radiation. Okay, so if a molecule absorbs a particular wavelength, okay, let me draw once again. Suppose we have a molecule, okay, we have a molecule and it absorbs a particular wavelength, okay, say lambda dash, okay, or nu dash, in terms of frequency nu dash, or in terms of wave number nu bar dash. The molecule absorbs a particular wavelength or frequency or wave number. Okay, then what should be the nature of the spectrum? Since it absorbs a particular wavelength, so the spectrum should be a line like this. The spectrum should be a line like this. Okay, because the molecule is absorbing a particular wavelength. Okay, but practically we do not get a line like this. Practically we do not get a line like this. What we get? We get the spectrum like this. Okay, we get the spectrum like this. Okay, we get this spectrum like this. Okay, I repeat, if the molecule absorbs a particular wavelength, we should get a line like this. But practically we do not get this line. We get the spectrum like this. So there is a width, you know, there is a width of the spectrum. Okay, if it were a line, then it would have been a point. If the spectrum were a line like this, then it would have been a point. Okay, but we do not get this, we do not get this, we get this, we get this. So there is certain width of the spectral line. Now why there is certain width of the spectral line? Okay, why there is width of the spectral line? Let us see that. So width of spectral line, width of spectral line. That means why in place of getting a point we get some region. Okay, that means there is some width. So why that happens? So width of spectral line appears mainly due to three reasons. One is called collision broadening. Collision broadening. Okay, one is called collision broadening. So you know, if there is gas, say there is gas, okay, there are gas molecules. They are constantly moving. So when they are moving constantly and they are moving at a random, so there will be collision. There will be collision between the molecules. Okay, Now due to collision, what happens? Their energy becomes uncertain. Okay, maybe when the collision occurs between the two, there may be slight deformation of the molecule. When the collision occurs between the two molecules, there may be slight deformation of the molecules, and thus energy is to some extent perturbed. So energy is to some extent become uncertain. So there is some uncertainty in the energy of the molecule. Okay, due to this uncertainty, so this uncertainty means this is equal to h del nu, because energy equal to h nu, h is constant. So there is some uncertainty in the frequency, and there is some uncertainty in frequency, that means there is some uncertainty in wavelength. So due to this uncertainty, there is broadening of line. Okay, this is called collision broadening. Now second factor is that the second factor is called Doppler broadening. Now you know Doppler effect. Suppose a train is moving like this. Train is moving like this, and you are here. Okay, so train is coming whistling. Train khone horn bojai ahi ase. Okay, the train is moving whistling. So when the train approaches you, then the frequency of the sound increases. Okay, frequency of the sound increases when the train approaches you. Then the train moves away from you, and when the train moves away from you, what happens? The frequency decreases. Actually, the train is emitting a definite frequency through its whistle. Okay, the whistle is ringing at a definite frequency, but what happens? As the train approaches you, it appears as if frequency increases, and as the train departs, move away from you, then what happens? Frequency decreases. Okay, similarly, so there are molecules here, they are moving at random. Detector is here, this is the detector. I told you last time, there will be detector which will detect the intensity of the radiation. Okay, now suppose the molecule is emitting radiation, and it is moving in this direction. Then what will happen? It is emitting radiation means it is emitting a definite frequency, but as it approaches you, as it approaches the detector, what will happen? Frequency will increase, just like here. Frequency will increase. If the molecule is moving this way, frequency decreases. So this is Doppler effect. So due to this also, there is some uncertainty in the frequency. Frequency may increase, frequency may decrease. Okay, it is emitting radiation, but it is moving in this direction. So it is moving away from the detector. So frequency decreases, frequency increases. So there is some uncertainty in the frequency. So there is some uncertainty in the frequency means the spectral line becomes wide. Spectral line becomes wide, just like this. In this spectral line becomes wide. There is some width of the spectral line. Okay, this is the second reason. Third thing is time energy uncertainty. Time energy uncertainty. Uncertainty. What is this? Suppose a molecule is here in the ground state. Okay? It is absorbing radiation and it is coming to the excited state. This is the excited state. Excited state, and this is the ground state. Suppose it is absorbing radiation, a definite frequency. It is absorbing a definite frequency and it is coming to the excited state. In the excited state, the molecule will remain for some time. The molecule will be here for some time. That means there is some life in the excited state. What is the, I say in case of electronic, suppose electron was in the ground state. The electron absorbs radiation and it comes to the excited state. And in the excited state, the electron will be there nearly for 10 to the power minus 8 seconds, nearly for 10 to the power minus 8 seconds in the excited state. Then it will come back, and when it comes back, it emits the radiation. So within this time, the molecule or the electron will come back to the ground state. Okay, that means there is some uncertainty in time. Uncertainty in time equal to 10 to the minus 8 seconds. There is some uncertainty in time. So due to this uncertainty in time, you know what is Heisenberg Principle? One form of Heisenberg Principle is this: h bar by 2. Normally what we write, del x del p is greater than equal to h bar by 2. Normally we write. Okay, this is the uncertainty between position and momentum, and this is the uncertainty between energy and time. So since there is some uncertainty in time for coming back to the ground state, there is some uncertainty in time for coming back to the ground state. Therefore, energy becomes uncertain. So what is the uncertainty in energy? Uncertainty in energy equal to, this is 4 pi into del t, because h bar equal to h by 2 pi. Okay, this. Now you see, h equal to 6.6 into 10 to the power minus 34 second. 4 pi equal to 3.14. Say electronic transition. Del t equal to 10 to the power minus 8 second. And I have already said energy equal to h nu. So del E equal to h del nu. Okay, so I can write here h del nu. So this h will cancel, this will cancel. So this is joule second, this is joule second. So cancels. So what is the frequency? Uncertainty in frequency equal to 1 by 4 into 3.14 into 10 to the power minus 8 per second equal to hertz. And you can simplify this, you will get the value. So there is some uncertainty in frequency. Due to that, the spectrum becomes this, not one line. Spectrum becomes this. There is width. Okay. So once again, just to repeat. So This spectral line, since the molecule absorbs a particular wavelength or particular frequency, we should expect a line like this, but we do not get this. We get spectrum like this. So there is width. And why that width occurs? Due to collision broadening, then Doppler broadening, then time energy uncertainty. Okay. So this is width of spectral line. Some problems may be asked like this. Okay, small problems, definitely you can solve it. Okay, you have to solve like this. If uncertainty in time is given, you can solve like this. Okay. Next, I talked about this, say log Beer-Lambert's law, I naught by I equal to, this is called absorption, this is equal to epsilon CL. C is the concentration, L is the path length, and epsilon is called the molar extinction coefficient. Molar extinction coefficient. Okay. So problems may be asked based on this formula also. Problems may be asked based on this formula also. Let me discuss one example. Just 1 minute. Let me discuss one example. Okay. Let me see. Problem is when a monochromatic radiation, that means having single wavelength, monochromatic radiation is allowed to fall on a solution of a compound with concentration 0.05 molar. The intensity of the incident radiation reduces to 1/5 of the initial value. If the path length is 1 centimeter, calculate molar extinction coefficient. So problem may be asked like this. Okay. Now, so you see how to solve this type of problem. So here you see concentration is given 0.05 molar, that is 0.05 mole per liter. Okay. Now if I convert into SI, this will be 0.05 mole 1 liter. 1 liter means 10 to the power minus 3 meter cube. 10 to the minus 3 meter cube. So this will be equal to 0. Into 10 to the power 3, that means it will be 50 mole per meter cube. So I am converting concentration, this is equal to C. Okay, so I am converting this concentration into SI. So in SI value will be this. Okay, then what is given? Say initial intensity, say I naught. Initial intensity, say I naught. Okay, I naught initial intensity, incident initial intensity of the incident radiation. So what has been told? The transmitted intensity equal to 1/5 of I naught. 1/5 of I naught. That is equal to I naught by 5. I naught by 5. Okay. So you see now, and path length L. Path length L equal to 1 centimeter, that is equal to 10 to the power minus 2 meter. 10 to the power minus 2 meter. So we know we have to use this formula. So I am to find out epsilon. Okay. So what will be the value of epsilon? Value of epsilon will be equal to 1 by CL into log I naught by I, that is equal to 1 by 50 mole per meter cube into 10 to the power minus 2 meter, mole per meter cube 10 to the power minus 2 meter into log I naught, and this is I naught by 5. So you just simplify this, and it will be just simplify. This is the 0.5. Okay, this will be 150. This will be 2 into log 5. Okay, this is meter square per mole. Okay, and log 5 means log 10 by 2 meter square per mole. So log 10 1, log 2 0.301. So you can simplify this. So you have to solve problem like this. Next, I would like to show you one spectrum. Okay, I would like to show you one spectrum. So you look at this spectrum. Okay, look at this one. This is IR spectrum. Okay, this is IR spectrum. Okay, you see these are the spectral lines. Okay, this is the IR spectrum of the compound citral. So you see this spectral line, you can call a band also, B-A-N-D, band. This band is very sharp, you see, very sharp, and intensity of this spectral line is very high. Intensity of this spectral, mind that, intensity of this spectral line, not intensity of the radiation. I repeat. So intensity of this spectral line is very high. This spectral line is quite sharp. But this is also spectral line, you see, this is also spectrum, band, this is also a band. But this band, intensity of this band is very low. Okay, weak. This is a weak band. Okay, so you see the difference. So intensity of this spectral line is very high, whereas intensity of this spectral line is low. Intensity of this spectral line, here you see intensity of the spectral line is very high. Okay, so absorption of radiation is also very high. Absorption of radiation is very high means intensity of the radiation will be low, because absorption is more, so intensity of the transmitted radiation will be low. Okay, intensity of the spectral line is more and intensity of the transmitted radiation is low because more absorption is there. Okay, here intensity of the spectral line is less. Intensity of the spectral line is less. Okay, that means absorption is less. Absorption is less means intensity of the transmitted radiation will be more. You see the difference. Now, why this happens? Sometimes intensity of the spectral line is more, sometimes intensity of the spectral line is less, sometimes in between. So why that happens? What are the factors on which intensity of spectral line depends? Let us discuss about that. So intensity of spectral line. Once again, don't confuse with intensity of radiation. Intensity of spectral line. Spectral line. What are the factors on which intensity of spectral line depends? Number one is called population of state. Population of state. This means that, so in spectroscopy what happens? Can we take a single molecule? No. We cannot take a single molecule. We take, say, a solution of this. We take a solution of the sample. We may take a solution of the sample. Solution. We may take a solution of the sample. And in the solution, there will be crores of molecules. Okay? There will be crores of molecules. So in spectroscopy, we cannot take a single molecule. That is impossible. What we take? We may take a solution of the sample. We may take a solution of the compound. In the solution, there will be crores of molecules. Okay? Crores of molecules will be there. Now, suppose these are the energy levels. This is the ground energy levels, ground state. This is the excited state. Excited state. So if there is one molecule, one photon will be absorbed. If there are two molecules, two photons may be absorbed. Three molecules, three photons may be absorbed. So if there are more molecules, more absorption will take place. Okay? If there are more molecules in the ground state, more absorption of photons will take place. More absorption means intensity of spectral line will be more. But if less number of molecules is there, number of molecules in the ground state is very few, then only a few photons will be absorbed. So the intensity of this spectral line will be less. So number of molecules means population of state. More molecules, population is more. Okay. So more molecules means population is more. Okay. Suppose this is the number of molecules in the excited state. In the excited state. Or I can say that this is the N1. N1 means number of molecules in higher energy state. Here number of molecules is n1. Okay, and here number of molecule is say n0. So this is given by a relation like this. This is Boltzmann relation. This is called Boltzmann relation. This. What is Delhi? Delhi is the energy difference. This is Delhi. Okay. So you see, this is called Boltzmann statistics. Okay, Boltzmann law. Okay. Now, what happens is that if you increase the temperature, then molecules will come over here. That means there will be less molecule in the ground state. Okay, at lower temperature, more molecules will be in the ground state. More molecules means intensity of the spectral line will be more. So this is known as population of state. Number 2 is transition probability. Number 2 is transition probability. Okay, so you know that say particle in one-dimensional box. For particle in one-dimensional box, what is the wavelength? What is the wave function? Wave function is this, half sine n pi x by a. And what is the energy? Energy equal to n square h square by 8 ma square. This is the wave function and energy of particle in one-dimensional box. Similarly, say harmonic oscillator. For harmonic oscillator also we have one wave function which depends on the quantum number v, and energy we have this expression. Or say rigid rotator. For rigid rotator also we have wave function. Wave function depends on two quantum numbers, L, M, and we have energy L into L plus 1 h bar square by 2i. Okay, so wave function means state. And this energy, state energy. Okay, so this is one state. Let me call it psi m. Okay, m may be m is the quantum number. Here what is the quantum number? Quantum number is n. And what are the values of n? Values of n may be 1, 2, 3 and so on. Here v is the quantum number. What is the value of the quantum number? 0, 1, 2, 3, etc. Similarly, L, M, these are quantum numbers. Okay, so m is the quantum number, and it is here say this is state. This state wave function is this. And what is the probability? What is the probability of moving the particle from this state to this state? What is the probability of moving the particle from this state to this state? Okay, what is the probability? That can be obtained. Say we have one integration, say psi m star, and this is dipole moment operator. This is the dipole moment operator, and psi n d tau. Okay, this is one integration, and square of this integration, that will give us the transition probability of transition. Square of this integral will give us the probability of transition. That means how much probability is there for moving from this state to this state. What is the value of the probability? for moving the particle from this state to this state. That is given by this. Now, for some values of m and n, this integral psi m psi n d tau may be zero. It may happen that for some values of m and n, this becomes zero. Then probability of transition will become zero. Okay? Now what does it mean? Probability of transition becomes zero. What does it mean? That means this transition from this state to this state is not possible. We may say like that, but that is not correct. Okay? When transition probability is zero, we say that this transition from psi m to psi n, this transition, probability of this transition is very, very small. But we cannot say that this transition will not take place at all. That is not correct. Okay? I repeat, when this integral becomes equal to zero, that means probability of transition becomes zero. Okay? It means that the probability of this transition from psi m to psi n is very small. Probability of transition is zero. That does not mean that this transition will not take place at all. Okay, I repeat, probability of transition becomes zero. This does not mean that transition from this state to this state will not take place at all. It does not mean that. This transition may take place. This is zero, but this transition may take place. But probability is very, very small. So in that case, intensity of spectral line will be small. But if this integral is not zero, this is not zero. Okay? Then probability of transition is not zero. Okay? That means this transition will take place. Now this transition will take place. In this case, we say that this is allowed transition. This is allowed transition. And in this case, transition probability is zero. In this case, we say that this is forbidden transition. Okay. So if transition probability is zero, it does not mean that the transition will not take place at all. Transition may take place, but probability is very, very small. So this type of transition is called forbidden transition. And if this is not zero, this is allowed transition. Okay? Allowed transition. Now, from this we get one thing which is called selection rule. So what is selection rule? Here m is the quantum number, n is the quantum number. Okay. For convenience, let me write it. Say psi n1 to psi n2. N is the quantum number. Let me, for convenience, for m1 I am writing n1. For n I am writing n2. Okay. So what is del n then? Del n equal to final minus initial. Okay. Now, if say, let me tell you, let me take one example. So this is a rigid rotator. This is rigid rotator energy. This is energy L equal to 0, energy 0. This is this is 0, okay, and this is E1 L equal to 1, okay. This is equal to, say, I discussed last time, okay. Okay, you see, we discussed. Say I call this okay, whatever it might be. See this, okay. Say so I write this as K. I write this as K. So energy becomes equal to L into L plus 1 K. Okay, K. So here what is the energy? L equal to 0, energy is 0. L equal to 1, energy 2K, 2, 6K, 3, 12K and so on. So this is 2K, okay. Then this is L equal to 2, this is 6K, E2, 6K, this is say L equal to 3, this is 12K and so on. So what is the energy difference? Energy difference is 2K. What is the energy difference? Energy difference is 4K. What is the energy difference? Energy difference is 6K and so on. Now for this transition, how much energy is required? 2K. For this transition, how much energy is required? 2K. Now 2K energy can be obtained from microwave radiation. We have already discussed. For this transition, how much energy is required? 4K. This energy also can be obtained from microwave radiation. For this transition, how much energy is required? 6K. This also can be obtained from microwave radiation. Now suppose this transition takes place. How much energy will be required? 6K. Now 6K energy is obtained from microwave. Okay, 6K energy is obtained from microwave. Okay, here what is the value of del L? Here what is the value of del L? Del L equal to 101. Here what is the value of del L? 2 minus 1, 1. What is the value of del L? 3, 2, 1. So for these transitions, del L equal to 1. But if this transition takes place, what will be the value of del L? If this transition takes place, what will be value of del L? Value of del L will be 2 minus 0, that will be 2. Okay. So if I write here L, I can write here L in place of N. I can write L. I can write L because these are the quantum numbers. Okay. Now these are the transitions. Del L1. This is the transition del L2. For this transition, how much energy required? 6K. For this transition, how much energy required? 6K. This is obtained from microwave. This also may be obtained from microwave. But it is found, doing calculation, it is found that when del L is 2, then this integral will become 0. When del L is 2, this integral will become 0. That means probability of this transition is very, very small. So this is forbidden transition. This may not take place. This transition may not take place. Even if this transition takes place, intensity of spectral line will be very, very small. Okay. But if del L is 1, then this is not 0. Del L is 1, this is not 0. That means this type of transition will take place. Allowed transition. Okay? Allowed transition. And selection rule is this. Selection rule. Selection rule is this. This is the selection rule. Not this. So selection rule will give you the allowed transitions. Which transitions are allowed? Okay? So selection rule will give you the allowed transitions. Allowed transitions. Okay? Not the forbidden transitions. Okay? So we will get selection rules when we discuss different types of spectroscopy. Okay? Now, so this is the introduction. Okay? Now let us discuss about rotational spectroscopy or microwave spectroscopy. Rotational spectroscopy or microwave spectroscopy. First, we consider the molecule to be a rigid rotator. We consider the molecule to be rigid rotator. So as we have already said, so suppose this is the molecule, this is the M1, mass is M, suppose hydrogen chlorine, HCl molecule, and this is the axis. This is the axis about which the molecule rotates. Okay? So this distance is R1, this distance is R2, and this distance is R. This distance is R. Okay. So obviously R equal to R1 plus R2. R1 plus R2, obviously. And since the two atoms, they are rotating like this, so M1 R1 must be equal to M2 R2. Since they are rotating like this, since they are rotating about this axis, so this is the condition. So what I can do from here, from this equation I can write, in place of R2 I can write R minus R1. Let me write this, M2 R minus R1. What I am going to do is that I will find an expression for R1. Okay? For R2 I am writing R minus R1. So or I can write M1 R1 equal to M2 R minus M2 R1, or R1 this side, so this will be R1 into M1 plus M2 equal to M2 R. Hence R1 will be equal to M2 R by M1 plus M2. Okay. Similarly, you can replace R minus R2 for R1 and you will get an expression for R2. R2 will be equal to M1 R M1 plus M2. Just this way, simple. Now, what is the energy? What is the total energy? Total energy equal to half M1 V1 square plus half m2 v2 square. Kinetic energy, potential energy is 0. Okay, now you know that v equal to r into omega, angular velocity. Omega is the angular velocity, so I can write here m r1, okay, v1, that is r1 v1 equal to r1 omega, okay, so r1 square omega square plus half m2 r2 square omega square, or I can take this common, half omega square I take common, m1 r1 square plus m2 r2 square, and this is nothing but moment of inertia. This is equal to half I omega square. This is equal to I, moment of inertia. I is the moment of inertia, okay. So I get this. Now what is I? I equal to m1 r1 square plus m2 r2 square. So I can write it like this, m1 r1 square plus m2 r2 into r2. Why I write this? Because for m2 r2 I can write m1 r1. So this will be equal to m1 r1 square plus m1 r1 into r2. So what I can do, I can take m1 r1 common, so this will be equal to r1 plus r2, and this will be equal to m1. What is the value of r1? Value of r1 equal to this is equal to m2 r m1 plus m2 for r1. For r1 I am writing this, and then r1 plus r2 r. So this is equal to m1 m2 by m1 plus m2 into r square, that is equal to mu r square. So I equal to mu r square. I equal to mu r square. What is mu? Mu is the reduced mass. Okay. Now for rigid rotator, what is the energy? For rigid rotator, what is the energy? Energy equal to, say, earlier we have written quantum number L, now we will write quantum number G. In place of L we are writing Z. Okay, just symbol is different, nothing else. Okay, J plus 1, and this is equal to h bar square by 2I. I equal to mu r square. Okay, what happens is that in case of microwave spectroscopy and IR spectroscopy, we write energy in terms of wave number. So you know energy equal to h nu. Okay, this is equal to h c by lambda. So E by hc equal to 1 by lambda. And what is 1 by lambda? Wave number. Okay, 1 by lambda equal to wave number. So wave number equal to E by hc, energy divided by hc, that will give us the wave number. In microwave spectroscopy and in IR spectroscopy, we generally express energy in terms of wave number. So in wave number unit, what we get? In wave number, what we get? So let me write this symbol, wave number. So this must be equal to this by hc. Okay, this is the energy in wave number, epsilon j, energy in wave number. So that is equal to this. So this will be equal to j plus 1 h bar square. So this will equal to h square by 4 pi square. 4 pi square, that means 8 pi square I, okay, into 1 by hc. So this will be equal to j into j plus 1 h by 8 pi square ic, and this is generally represented as b, rotational constant, b equal to this is equal to b, rotational constant. Okay, so energy of the rigid rotator in wave number unit is this much. Okay, so once again, so these are the energy levels. Z equal to 0, energy is 0. Okay, energy is 0. Z equal to 1, Z equal to 1, so energy equal to 2b. Z equal to 2, J equal to 2, so energy equal to 6b, and so on. So these are the energy levels. So in spectroscopy, we basically need two things. One is energy expression. After that, what we need? We need the selection rule. Why we need the selection rule? Because from the selection rule, we will know which transitions are allowed. And from the allowed transitions, we can find out the energy required for the transition. So ultimately, we are going to calculate the energy required for transition. Okay? We are going to calculate energy required for transition. For that, we need two things. One is the energy expression, the other is the selection rule. Selection rule will tell us which transitions are possible. Okay. Now in this case, the selection rule is this: del j equal to plus minus 1. That is, transition may take place from j equal to 0 to j equal to 1, or j equal to 1 to j equal to 2, or 2 to 3, 3 to 4, like that. But this type of transition, say j equal to 0 to j equal to 2, not allowed. Forbidden transition. So we are not going to calculate the energy for forbidden transition. We are going to calculate the energy required for allowed transitions. Okay. Suppose this transition, how much energy is required? For this transition, how much energy is required? Energy required equal to, here 2b 0. Okay. So del E J, that is equal to E1 minus E0, that is equal to 2b. Let me write it. So for this transition, j equal to 0 to j equal to 1. So for this transition, how much energy is required in wave number? E1 minus E0, that is equal to 2b0, so 2b. Okay. For this transition, how much energy is required? So del Ej, that is equal to E2 minus E0. Okay. So how much energy? 6b, sorry, this is E1, 6b minus 2b, that means it is 4b. So these are the levels. Okay, these are the levels. Z equal to 1, 2, 3, 4, so on. So for this transition, how much energy is required? 2B. For this transition, how much energy is required? 4B. For this transition, how much energy is required? 6B. And so on. Now we can find out a general expression for energy required. Say transition is from, for the transition Z to Z plus 1, Z to Z plus 1, 0 to 1, 1 to 2. Okay, how much energy is required? Epsilon J plus 1 minus epsilon J, that is equal to J plus 1, J plus 2 B minus J into J plus 1 B, and that is equal to J plus 1, I can take common, so J plus 2 minus J, so this will be 2B or 2B J plus 1. So this is the general expression. So energy of microwave radiation. Microwave radiation. Say new bar. Energy of microwave radiation in terms of wave number must be equal to 2B J plus 1. So this is the general expression. Okay, this is the general expression for transition. Okay, you can see here this 0, 1, 0, so 2B, you see, 0, 1, so this is 0, so 2B energy required, 0 to 1. Oh, sorry, this is 0, this is 1, sorry, this is 2, this is 3, and so on. Okay, so this is the general formula. Okay, so graphically we can show this. So this is the energy of microwave radiation. Okay, the molecule is rigid rotator. For this transition, how much energy from the microwave radiation will be absorbed? For this transition 0 to 1, for this transition, how much energy of the microwave radiation will be absorbed? 2B. So we will absorb a spectral line at 2B. So this is 2B. Next, for this transition 1 to 2, for this transition, how much energy is absorbed? 4B. So we will observe another spectral line at 4B. This transition, we will observe another spectral line at 6B. This is the first spectral line, second spectral line. So next, for the next transition, we will get one absorption line at 8B, and so on. That means if the molecule is rigid rotator, we should observe spectral lines. At a constant separation of 2B. What is the difference? 2B. What is the difference? 2B. What is the difference? 2B. If the molecule is a rigid rotator, then we should observe spectral lines at a constant separation of 2B. So this is the microwave spectrum. This is the microwave spectrum of a molecule, considering it to be a rigid rotator. Okay. Now from this result we can calculate the bond length. We can calculate the bond length of a molecule. We can calculate the bond length of a molecule. Let us see that. Let us see that. Now question is the first line in the rotational spectrum of carbon monoxide appears at 3.84 to 35 centimeter inverse. Calculate bond length. Calculate bond length assuming rigid rotator, using rigid rotator concept. Calculate bond length using rigid rotator concept. Okay. Now you see how to solve this first line. Where we get this first line? 2b. So 2b must be equal to 3.84235 centimeter inverse. Hence we get the value of b. What is the value of b? 1.921175 centimeter inverse. Okay. Now what is b? b equal to h by 8 pi square IC. That is equal to 1.921175. We can convert it into SI. Okay. Now centimeter, let me show you centimeter inverse. That is equal to 10 to the power minus 2 meter inverse. Okay, inverse. That is equal to 10 square meter inverse. 10 square meter inverse. Okay. So this is equal to 10 square meter inverse. Okay. Now we know the value of so from this we can find out the value of I. What is I? I equal to h 8 pi square b c, that is equal to 6.6 10 to the power minus 34 joule second, 8 into 3.14 into 3.14 into 1.921175 into 10 square per meter, 10 square per meter C into 3 into 10 to the power 8 meter per second. So calculation will be a bit longer, but you can calculate. 6.6 8 into 3.14 into 1.921175 into 3 into 10 to the power into 10 to the power how much? 10 minus 24 10 to the power minus 24. What will be the unit? Joule into Newton, joule second meter. joule second meter. Okay. So you can find out this. Joule equal to Newton into meter second meter. Newton equal to kg meter per second square into meter second meter. Okay, so kg meter square. Okay, I mu mass into r square, kg into meter square. Unit should be kg meter square per second square. Joule second. Okay. Okay. Second. Newton into meter, joule second, Newton into meter, meter inverse. So meter, Newton into meter second meter, kg meter per second square meter. Is there some mistake? So B equal to this BC. Oh, meter per second, there is meter per second, no? There is meter per second. So per meter second, per meter second. Okay, now this cancels. So this is equal to kg meter square, kg meter square. Okay, kg meter square. It will be kg meter square. So you have to simplify this. Now what is I? Now I equal to mu r square. So what is the value of mu? Mu equal to m1 m2 by m1 plus m2. Say carbon atomic mass is 12 amu. Oxygen atomic mass is 16 amu. Atomic mass 12 amu, 16 amu. So this is equal to 12 amu into 16 amu, 28 amu. So amu cancels. So 48 by 7 amu equal to 1.67 into 10 to the power minus 27 kg. 1 amu equal to this much kg. Okay, so we know the value of I. Kg meter square. We know the value of I. So this is equal to 48 by 7, 1.67 into 10 to the power minus 27 kg into r square. So you just simplify, you will get the value of r square. R square will be in meter square. Kg cancels, meter square. So then you take the square root and you will get the bond length. This is the bond length. Just simplify and you will get the answer. Okay. So this is how you are to solve this type of problems. Okay. So let us stop here today. Next we will discuss some other aspects. Okay. Thank you.